geographers, who is Mark Blacksell. This is part of the Mark Blacksell Memorial series of lectures. Some of you will know that Mark Blacksell was both the head of geography and also the dean of the faculty here. It's fitting then that we also have today to give our Mark Blacksell Memorial Lecture Professor Dan Charman, who started, I'd like to say, had the benefit of starting his career at the University of Plymouth, is now Dean and Pro-Vice Chancellor at the University of Exeter, or as we refer to it, the other place down the road. I remember Dan coming, I think, very early on. We went for lunch at the pub, which was possible in those days. And I remember Dan arriving with a tie, and that kind of lasted the lunch, I think, and then left. I think the period during which Dan was part of the university was one marked by a lot of change. We went through several names of departments. We went through several faculties. Throughout that period, Dan's focus was on the long-term change in ecosystems, in particular in relation to climate change, and I think that's what we're going to hear about now. So, Dan.
Right, so I mean, first thing to say is thank you very much for asking me to do this. It is truly a tremendous honour to do this, and even more so since I see this room completely full of people, which is, I'm afraid to say, is not what I expected, frankly, when John asked me to do this. So it's great to see such a lot of people here, and it makes me feel even more humbled by the invitation to come and do this talk. I think I was last in this lecture theatre teaching first year biogeography in 2008-9, I guess, sometime around then. So I hope tonight you're all a little bit more awake than the students who are at 9 o'clock on a Monday morning for biogeography. I also hope that what I've got to say is perhaps a little bit more interesting than what I had to say to first year biogeographers, or maybe not, who knows. Maybe what I had to say to them then was absolutely fantastic and stimulating, at least I hope so. I also had an office just across the road in Queen Anne Terrace, I think in 1991. I was here from years 22 of the department to year 40 of the department I worked at. So I was here for almost 18 years in the end. And we did move around, and there were some changes. The way you phrased it, Ruth, was almost as if it were my fault that there were all those changes in names and organisation. It really wasn't. I just went along with it. The second thing I'm particularly pleased to be here about is really just to refer to the Mark Blacksell Memorial Lecture. I mean, Mark was, I was here all the time that Mark was here. It's interesting, actually, when you look back on stages of your career, you only realise who the people were who had most influence on you when you look back. And Mark is undoubtedly one of those people. I think left an indelible mark on pretty much everybody who worked with him. He was, as many of the obituaries will have said, he was very larger than life in all sorts of ways. But he had a tremendous passion for academia, tremendous passion for students. He genuinely cared about other people. And I think one of the things that I'll always take from Mark is that fundamentally universities are about people and about caring for those people and valuing their contribution. I think it's a lesson that many universities could take a little bit more seriously. And above all, I think he taught me a number of things, which is take your opportunities, think big, do it with gusto, and do it with a bit of fun. And if you do that, you're not going to go far wrong in your career. So it really is a tremendous pleasure to be talking in Mark's name. So what am I going to do tonight? I'm going to talk a little bit about wetlands and climate change. I'm slightly cognizant of the fact you've already been sitting here for a little while. I wasn't quite sure what the timetable was going to be. I think I've got about 45 minutes, but I may, depending on how things go, I may skim over a few things just to make sure you can get to your glass of wine on time. I don't want to keep people from that at all. So the reason I want to talk about wetlands and climate change is that one of the big changes that's taken place, particularly in climate change science, since I was started teaching on climate change. We had a course called Man, Environment and Climate Change. What a dreadful title. We'd never get away with that now. Not very, EDI compliant. But although it was a dreadful title, it wasn't a dreadful course, and it was about climate change. At that stage, there was a lot of, we're in the very early days, the sort of early 90s, and climate change prediction, especially, or projections, was really its infancy. And it was all about how the atmosphere is changing and how it's going to change climate and what impacts that will have on the Earth, or on people and on the Earth. What we realise now, of course, is that the Earth itself reacts in various ways to climate change and actually has a so-called feedback effect on the climate itself. And wetlands are one of the systems in the world that's right at the heart of that kind of action. Climate affects wetlands, but wetlands also affect climate. And some of that will come out in what I have to say. The other thing I want to say is I will not have lots and lots of graphs, there are a few, but there are some maps and there's lots of pictures. So hopefully you won't get completely bored and you can just look at the colours and the pretty pictures, if nothing else. So, what makes a wetland? Well, the most obvious thing and the most correct thing is simply water. You know, it's kind of obvious, but it's true. Where the water is, how much of it is, how much it fluctuates, how warm it is, what the nutrient conditions are, all of that is important, but fundamentally wetlands have water. So there's lesson one. If you don't go away with anything else, go away with that. Perhaps more critically, it's actually about the interplay between land and aquatic systems. And this just shows across, you know, kind of typical kind of variation from lots of wet stuff on the left to a bit drier on the right. There's water in the whole system, but it's these transitions between the terrestrial and the aquatic that become really important. But wetlands don't have to have lots of water. This is just up the road, so this is just a Google image grab from of northern Dartmoor, Fernworthy plantation in the background. Dartmoor is most of it is a wetland. Most of the northern part of Dartmoor can be considered a wetland, but it looks pretty dry until you start to walk on it, and there's water in the entire system. So wetlands are wet, but they can be, you know, a bit dry as well. They can also be completely covered in forest. This is in Indonesian Borneo. This is the Borneo Nature Foundation research site there, and underneath that forest is a huge depth of very wet, sloppy peat, 15, 16, 17 metres of it. The forest is growing on this, what is effectively a substance which has fewer solids in it than milk, in practice. Extraordinary. And wetlands, the water in wetlands can also be there as ice. And lots of wetland systems, it's the ice that controls what's actually happening, and the ice that provides the important interplay with climate. So on the left there you just see a chunk of the material that's been drilled out from under the ground, and this mixture of kind of mucky peat and ice. And on the right, you probably can't really see it, but in that little cavey bit there's a big block of ice which is gradually melting in these conditions, and we'll actually see a subsidence of the surface as it melts, changing the nature of the system. So we can have ice in these places as well. I'm just going to try and run this. Just mute the helicopter a minute. So the other thing about wetlands is they can be enormous. I mean, quite incredible scales, particularly in the northern high latitudes, in the boreal and the Arctic systems. This is just Tim. Where's Tim? Tim was on board this helicopter at the time as well, actually. This is in Quebec, on the north shore of the St. Lawrence Seaway. This goes on for miles and miles and miles. Right up to really to the northern part of Quebec, northern part of Hudson Bay, almost without stopping. This mixture of water and slightly dry areas in between, one or two hummocks where you get a little bit of tree growth, but essentially a vast wetland system holding huge amounts of water and huge amounts of carbon, which is something I'll come on to. Wetlands can also be small. They can be sort of semi-created, as this one is. So this is the London Wetlands Centre, well worth a visit. It's abandoned reservoirs converted into an urban wetland, and of course, you know, in many ways, much more valuable area for area than perhaps the same part of one of these northern boreal systems. It's a fascinating place to go and visit. Wetlands also accumulate stuff. All sorts of stuff gradually builds up with wetlands. Mud, peat, gravels, all sorts of stuff. Students absolutely love enjoying it. It's one of the great pleasures of field teaching on this subject with students. They really get into it, literally in this case, not just hands and bodies, but also faces. I think some of them you can see perhaps on the right, slightly less enthusiasm from girl again there, but you notice there's always, in a group of students, there's always a clean one at the end. There's always one clean one at least, and then varying degrees of enthusiasm amongst the others. But it is a fabulous thing. It's what's under the ground in wetlands is critically important for the climate, and I'll come on to that, partly because of this accumulation, particularly of carbon, which is fixed from the atmosphere ultimately. So they're a huge carbon store. I'll be talking a bit more about that in a few minutes. So where are they? Well, I like this map, not because it's particularly accurate, and it's definitely not very precise, but it at least illustrates the main points. It's really just a shading of the Earth according to where the dominant areas of peat and wetland systems are. Two things to really point out about it. Across the northern high latitudes, particularly north of about 40 degrees, then there are those are where the dominant large areas of wetland systems are. And then through these tropics, there's a sort of sporadic scattering of wetlands. The map is a sporadic scattering, partly because people are a bit still unsure about where they are and quite how much of it there is and so on. So it's extremely inaccurate in those areas. And then as you go down into the few land areas there are in the sort of temperate zone of the southern hemisphere, around 40 or 50 degrees south, so Patagonia, southern part of Australia, Tasmania and New Zealand in particular, that's where you also get more wetlands. You clearly don't get quite so many wetlands in some of the other, the drier, particularly the Mediterranean and arid and sub-arid parts of the world, but there are, even in some of those places, there are a few wetlands around. So I'll try and take you on a little bit of a tour of some of these systems, concentrating on those I've been lucky enough to visit, perhaps a bit more recently as well. So it's a bit of a snapshot, but I'll try and take you through them and think about what's happening to them now. So a little bit of this is about what's happening to them now in relation particularly to recent climate change and what might happen in the future. So here we are, fundamentally in wetlands. There are a couple of things that are happening. You've got that vegetation in the top left which is growing on the surface, in this case a sort of fresh mossy growth. Over time what happens is that builds up at the surface and it doesn't decay completely. So what happens in this bottom part here is you get, is this the only pointer I've got? Is there I'll use this. I'll just use the cursor again. Yeah, thanks Tim. So what you've got is this surface vegetation growing. Then at the bottom here, gradually you can see the layers building up, representing different periods of time and different conditions, and that builds up into these enormous depths, up to the point where this one is probably a bit dangerous in terms of digging to that depth because it's going to collapse at some point. So that's a little bit of cross section through a typical wetland in Northwest Europe at least. Not many diagrams, this is one of them, but there's only three kind of components here that I want to emphasise, and they're circled in top. This is about how carbon moves between particularly the wetland and the atmosphere. So, three things happening. Carbon dioxide is going into plants through photosynthesis and it's being stored in the surface, either in the vegetation and recently dead material as peat. Some of that is decaying and going back out. Oops.
Sorry, that's me, no, sorry.
All right.
I could, the slide change is definitely working. The pointer is not. Apologies.
I'll just use it. So what's actually happening so some of that material is decaying and going back out to the atmosphere. What's happening, of course, is there's an imbalance. There's more going in than going out, which is why peat builds up. That's the fundamental process. The other thing that's important to note is you've got this other molecule. I should have written it on here, it would have been easier. Methane. So a few clever people in the audience thinking, yeah, I knew that. But methane is also produced by wetlands, and that's really important in terms of climate change and the carbon cycle. So just remember that there's carbon dioxide going in, sucking it up, creating this sink of carbon. There's also a bit of carbon coming out, particularly as methane. Just to give you an idea of the magnitude of this, these figures will mean nothing to you, but the carbon pool, the total amount contained in peatlands globally, is generally reckoned to be about 600 gigatons. That's 10 to the 9 tons, billions of tons, 600 billion tons. That's about the same carbon as is held in the entire global atmosphere. Or it's about the same amount of carbon as held in the entire global vegetation, standing biomass of global vegetation. So it's a really significant amount that's held onto the ground. You can see that somebody's kindly dug up some of it here and left it exposed to the surface to decay or get used for something, but that's what it looks like when you dig it up. The rate at which it goes into the ground, the sequestration rate, is actually quite small, but it's been happening for thousands of years. Again, don't worry about the figures there, but it's quite small, a 20th of a gigaton per year. But it's because it's doing it for a long time, it's built up this huge stock. And then in terms of the amount of methane going into the atmosphere, that's roughly half to 2/3 of what we produce through anthropogenic emissions. So you'll hear in a lot of debate at the moment about cows and sheep and methane production and how much meat we should be eating and so on. Actually, wetlands are a natural source of methane which contributes far more, in fact, than agriculture. So, they're important in terms of the global carbon cycle. On to some different parts of the world. Here's a little test for you, not test, a guess, an interesting mental experiment. Where does that remind you of? Think of that, get that in your head. If it reminds you of somewhere, what animals might be in the foreground of it? So, I'll leave it. This is a rhetorical question. I expect you to you can shout out if you want, but just think about that. It's penguins. How many people have penguins in their head? Not very many, I would guess. I want to talk a little bit about wetlands in cold places to start with. So the ends of not quite the ends of the Earth, but getting there. This is in the Antarctic. This is the Antarctic Peninsula. And there are, surprisingly, wetlands in these really extreme environments. And one of the reasons that we've been keen to work on them is because it's in these really extreme environments that they're most sensitive to changes in climate and particularly to temperature. And that's principally why we've been working on them. These are the kind of places, this is what it looks like. The top long thin graphic there is a place on Elephant Island. A lot of you will probably know Elephant Island from the story of Ernest Shackleton. So Shackleton's camp, where he had to stay for quite some substantial time, and where he eventually came back to, having voyaged across to South Georgia in a rowing boat, was just around the corner from here, actually, just a couple of kilometres off to the right. What you see there is a typical snowy landscape, but if you look very carefully, perhaps we should have dimmed the lights a bit more, but you might see little browny, kind of greeny splodges on there as well. Those are effectively peat-forming systems growing in this very extreme environment. The middle photograph at the bottom is what they look like, or what some of them look like. They're quite pretty, they're incredible splashes of green amongst the quite barren landscape. And then you get these, they're used by wildlife. There's a great skewer on the left, and occasionally you're interrupted by a seed as well. I have to say they don't do a lot for the preservation of the moss banks, but they can be quite entertaining. We were working on the top of this hill here somewhere, and on the top of this peak here, to do some work there. And I'll just tell you why we were doing that in a minute. But this is, can I just mute it again? Don't want the sound of a drill. When you get up close, this is what they look like. You can see that the bank at the left, the top left there, how deep they are. This is an accumulation of about 3 meters of material, accumulated over 4,000 to 5,000 years. They're almost completely solid with ice, so that's solid ice below about 15 centimeters below the surface, and you have to drill down to sample them. And when you do that, when you finally get it out of the ground, you can see here the folks are struggling a little bit with that, because as soon as you stop drilling, it freezes itself into the ground. what you actually get is what you see on the bottom left there, these cores of frozen material, which you then rush back to the ship and put them in the freezer. So that's what they look like, that's how we sample them. Why were we doing that? Well, principally, we were inspired by this kind of data, which we were looking at more than 10 years ago now, which this shows it's an unfamiliar orientation, so you have to get the orientation. This tail coming down here is the Antarctic Peninsula. So the South Pole is off to the top right here, the tail's here. The Antarctic Peninsula is known to be one of the fastest warming places on Earth. And at the time, actually, it looked like the Antarctic Peninsula alone of the Antarctic was a real hotspot of temperature increase. So that's expressed as degrees centigrade per decade warming, so about 0.3 degrees per decade warming, which is pretty fast. We subsequently realised that actually the warming is present over a much bigger area of the Antarctic, right across the West Antarctic area, in fact, which is one of the reasons for lots of concern about ice sheet stability in that area. But we were inspired particularly to look at the response of the biological systems to this rapid change on the Antarctic Peninsula. And I said I wouldn't show many graphs, and well, there are one or two. This is one of them. What we did was we tried to measure, by using the preserved remains in those cores, what the changes in the biology of the system have been over the period of rapid warming. So we did three measures here. One is microbial productivity, which we measured through the preservation of these shells of single-celled microbial organisms, which are preserved over time in the moss. We measured the growth rate of the mosses, and you can see they form these long strands which go down quite some way. We measured that both as the rate of incremental length growth, but also as the rate of mass accumulation. And we did that on a number of different places along the Antarctic Peninsula. What you can see, each one of these lines represents a separate site, a separate location on the peninsula, and they summarise really the biggest change in the record. And you can see through time they all occur in this period of the last part of the 20th century, which was experiencing whether this rapid warming was being experienced. So what we're able to conclude is that already, due to that warming that's been recorded in instrumental climate data, these systems have undergone this kind of state shift. They're suddenly kind of motoring again because of this warming up. And in fact, we also think that these systems now are starting to spread and become much more dominant parts of the Antarctic Peninsula. And it leads us to think about a kind of greening of the Antarctic is starting actually in that part of the world. Staying cold, but going to the other end of the world, going to the Arctic. This map, for no particular reason other than to remind me that I'm talking about the Arctic. So the green patch is the sort of wetland area. The other stuff is kind of irrelevant to what I've got to say tonight, but it gives you an idea of the way in which the wetlands kind of have this ring around the Arctic and the boreal parts of the world. This is a place in Lapland, which I was in just this September. And this little bit of drone footage shows us moving from the drier upland area to one side over this wetland area. You'll see the pale patches there are kind of quite watery, waterlogged areas dominated by grasses and sedges, and then you get these slightly drier areas in between, a few small trees and shrubs. We're almost at the tree line in Lapland here, so we're right up north, close to the Arctic Sea. And as we move across this system, you can see that there's this other dark area on the horizon. It's going to stop in a minute, I think, and once we get there, you will see this dark area that's coming closer towards us now. That dark area here is not an area that's actually drier because it's got rock or solid ground under it. It's dry because it's underlain by major formations of ice. These systems are called palsas. They've got big blocks of ice forming within them. And as the ice forms, because when water freezes, it expands, it pushes up the surface. and that creates a completely different kind of hydrology and vegetation. One of the things that's happening in the Arctic is that those ice blocks are melting, the ice is melting, leading to a collapse of these systems, and we'll see some consequences of that in just a minute. If you go to the high Arctic, so I would describe Lapland as the low Arctic, if you go further north, right up to the high Arctic, so here we are, this here is Svalbard. So can you see that? I should have put a bigger map up. Some of you are quite a long way away from the screen, but nearly 80 degrees north, so pretty much as close as you can get to the North Pole and still be on land. In fact, one of the launch pads for some of the big expeditions earlier in the 20th century to the North Pole. The kind of landscape you get there is much, much more barren. Mostly rock, mostly ice, not much vegetation. But there is some. And what you've got there is these patches, these bright green patches stand out, and some smaller patches are present as well. And we were interested in these because what our hypothesis is that these might actually be the points at which new formation of wetlands is starting to occur. The Arctic is interesting because, again, it's a very rapidly warming area of the planet. So you can look at all sorts of data on this, but this plot essentially shows the warming over the 20th century, the trend in global warming over the 20th century in different parts of the world. You can see that the dark purple splodges are mostly up in those northern high latitudes. Depending on where you are in the Arctic, it's probably warming at roughly twice, sometimes up to 4 or 5 times faster than the global averages. So in Svalbard, some of the temperature records show almost a 4-degree change over the last 50 years. So really rapid change. You know, we're very shielded from it here in the temperate zone, but if you go to the Arctic, it's visible, it's observable within the lifetimes of even quite young people. And you know, it's quite frightening actually to go up there and look at what the impacts are of climate change already, notwithstanding what might happen over the next 100 years. The point is the Arctic is warming rapidly. What happens when those blocks of ice melt? What happens is you get these big pools forming. There's a picture here with trees in it because it's easy to see what's actually happening there. The whole thing is collapsing in. The trees are folding in on themselves. Some of them are already dead. And you get these pools forming, which then has the potential to release methane. And in fact, this kind of catastrophic view of melt in the Arctic has been the predominant one in the literature, for good reason, and it's certainly a very important process. On the other hand, what we think is also happening, and here's my colleague digging away in the peat to get samples, with enjoying the local wildlife, which is mostly mosquitoes in this area, so he's got his cover on. What actually happens is when you get this infill of vegetation, you get renewed peat growth. So when it's pushed up by ice, it's very dry, it's really accumulating very, very slowly. What actually happens over on the right here, if you look at this, you can hopefully this transition is observable here. You get a dark layer below, which is what was accumulating when it was high up and was taking a long time. This fresh stuff on top accumulates very, very quickly. So you've got new carbon being put into the system as a result of this melt. So there's a bit of balance, and we're getting to understand the whole system a little bit better now than we were a few years ago. Oops. And the other question, which I've already alluded to, is the question about whether or not Arctic wetlands are actually spreading and could potentially spread even more in the future. I'll come back to this at the end, but what we're doing here in this kind of work is we are using both satellite imagery to demonstrate that we can already see the spread of wetland vegetation, and then on the ground actually using these looking at these shallow accumulations of peat to work out when they formed, how fast are they spreading, and whether or not that's relatable with this increases in temperature. So lots of change going on in the Arctic, and it feels like the sort of place, if you go back to the same place in 10 years' time, you would really notice a major difference. Moving to warmer places. Going to the tropics is a very different kind of, it's a very different kind of place. And for a start, the vegetation obviously is much lusher. It's much more difficult to work in actually in many ways, but it's tremendously exciting. And we sat in this forest the swamp forest in Borneo, and just listen to the gibbons and the birds, and it was really quite a magical place to work in. Fantastic wildlife, you know. This thing on the left is some kind of weird caterpillar. I mean, I don't know what it is. We didn't see it again, and nobody could tell me what it was. I don't know. These pitcher plants, each one is the size of a breakfast bowl. You know, they're sort of monstrous things. You've got orangutan, you've got amazing butterflies, you've got one or two snakes as well, which makes life interesting. But you've also got people. You know, people are an important part of the systems here, particularly around the edges, particularly for fisheries in the rivers. They are also tremendously mucky places to work. We were there in the dry season and it was wet. I really hate to think what it's like during the wet season. And this is the point I was making earlier on. You get these big trees underlaid, and this is a sample from underneath the ground, underlaid by sloppy mud. And it's a bit of a wonder how structurally the thing actually holds together. So they're really quite incredible places to work in, difficult places to work in, but great fun. The big thing about the tropics is we really don't know where all of these places are, partly because they look like other forests in many cases. So people haven't really discovered all the places that there are. This is quite a big area in the Congo Basin that was only properly described in 2017 and added about 30 gigatons of carbon to what we know of in the tropics by a group from Leeds. So these kind of discoveries are happening not regularly, but they're happening frequently enough for us to realise that we don't know all there is to know about tropical. In terms of recent changes in tropical peatlands, the biggest changes are due to human activity. And there's some quite sad stories. I'm going to get on some more hopeful stories at the end, but there are some quite sad stories about tropical peatlands. That top left photograph is part of the so-called Mega Rice Project, which was established by the Suharto government in Indonesia in the 1990s, where they tried to convert large areas of swamp forest to rice growing. You can see the little dots are actually little huts for people to live and work in. Failed completely. Turns out rice doesn't like growing on these kind of peat soils. Completely abandoned, but the drainage is still there, the kind of waterways are still there, which mean that actually they're drying out. Combine that with last couple of decades really now, particularly the last 10, 15 years of oil palm plantations, a lot of which is on peat soils, then what we're seeing is a drying out of a lot of the tropical wetlands, particularly in Southeast Asia, particularly in Malaysia and Indonesia. And the result of that is that these systems then become much more prone to fire. And this satellite photo at the bottom just shows the whole of that area covered in smoke. Flights get stopped, people's health deteriorates. It's a really major regional pollution problem. And it's becoming more frequent and worse pretty much every year. It's also, again, releasing huge amounts of carbon to the atmosphere. And Indonesia is, I think, the second biggest emitter of carbon dioxide if you take the fires into account. In one single year, in a particularly bad year, there was about 2.5 gigatons of carbon released from this region, which is between 25 and 40% of the total anthropogenic emissions for that year. So really big impacts on potentially on the climate. Let's come a bit closer to home. Wetlands in between, I'll call them, which is just, what I mean by that is they're not at the extreme heat, they're not at the extreme cold. They're in this ring around the world. Top left, you've got an audience member, you've got Tim Daly in one of the southernmost raised bogs in North America, in Maine. Top right is a sort of aerial photograph in the autumn in Estonia. Bottom left, you get these amazing systems in Patagonia, which are dominated by a single species of moss, which is bright red. And if you ever get the chance to fly into Ushuaia in Tierra del Fuego, look out the window and you'll just see these big red splodges scattered around the landscape, and this is what they are. They're the wetlands dominated by this red species of moss. Bottom right is New Zealand. Again, it doesn't look like a wetland, but underneath there is about 12 metres of sediment, and actually underfoot it's pretty wet and scrubby, despite what it actually looks like. So wetlands in between. Well, this is the part of the world which has really suffered most from human impacts. There have been some impacts of recent climate change on the system, but actually most of the impacts are human-induced. This is perhaps one extreme in the Netherlands, where it's purely intensive agriculture. There are other impacts as well. So we are not particularly good in our behaviour still of the use of peat both as a fuel but also as a horticultural product. This bag of New Zealand's sphagnum moss was photographed in a Newton Abbot nursery. How bizarre is that? We've got the ironically named Evergreen Irish Moss Peat lorry as well there, delivering its load from Irish peatlands. And bottom right, that's Patagonia, that's Tierra del Fuego. You might think it's remote and so on, but actually lots of digging for horticultural peat going on there. And what actually depresses me, and this is just an aside as a personal appeal, in about 1990, B&Q had a programme of having all of their products peat-free. Roll the clock on 30 years, you go into B&Q now, you'd probably find it hard to find a bag of peat-free compost, let alone one that was any good. It's quite depressing in the way in which we haven't really moved on in our use of horticultural products. And actually, this is a personal urge for anybody next time you're in a garden centre, stay away from peat, please. In other parts of the world, there's also been rapid change. In parts of the world where you might think that perhaps the environment might be a little bit more pristine, a little bit less damaged. So if you go to New Zealand, you will see areas that look as if they're reasonably natural, and we worked in this one, which is in Tangongi, in the very northern part of New Zealand. We went there with the local iwi, the Maori people who lived there, because it's a sacred site for them. So it's their wetland. They have two main totemic symbols in the landscape. One is the wetland and one is the mountain. And we also gave them this picture of one of our mountains. It's one of those GWR posters from Dartmoor. And what was really nice was a couple of years later, we went back. It was hanging up in the marae in the village hall. So it's very valuable culturally. They call it the lake. It's often translated as the lake. We thought, why? They keep talking about this lake, and in fact, many of the older generation remember when it was still a lake. What happened in the 1920s was it was drained, dug over for exploitation, particularly of extraction of kauri gum, but also for agriculture, which didn't work. And now what you see in much of northern New Zealand, the Hauraki Plains area in particular, is you see a lot of cows. They're actually grazing on grassland, which is over the top of drained wetland areas. Sometimes some blueberries as well. So but very converted landscape, very unnatural landscape in New Zealand as well. I'm going to finish off then to get us in time for our wine, which I think was due at 7. I'm going to finish off with just 5 minutes talking about wetlands under future climate change. What might happen in the future? So the plots on the left, some of you, if you've seen any of the reports of the Intergovernmental Panel on Climate Change, and I know some of these figures are more widely used than many sort of scientific documents, so people might have seen these. Just look at these two ones on the right here, because they're easiest to see the regional patterns, which is really what I want to talk about. The top one is one of the projections of temperature change to the end of this century. The bottom one is projections of percentage in precipitation change to the end of this century. And I've just put the wetlands map on the right there just to remind you where the wetlands are. If we look forward to the next 90 years or so to the end of the century, in terms of temperature, the Arctic and the boreal and Arctic region will still be one of those areas of the world which is accelerating in terms of its temperature change. In this scenario, up to 11 degrees change. It is also, if you look at the bottom plot, one of the areas which will experience the most significant increase in precipitation. So very much warmer, very much wetter in those parts of the world. Go to the tropics, and the areas of wetlands in the tropics, it will be warmer, The interesting thing about the projections of precipitation in the tropics, which are going to have a major influence on wetlands, is they're very variable. So if you look at West Africa, it could be a decrease in precipitation. If you go to East Africa, it could be an increase. If you go to Indonesia, it's kind of the jury's out a little bit because it depends a little bit on how El Nino evolves over the next 90 years. So there's a lot of variability, and my point really is to say that the wetlands are in the parts of the world which could experience some of the most dramatic changes in the future. So what might happen? How do we work this out? Well, this is a bit of a complicated plot, which I'll just try and explain. This is, I think, the only complicated plot. This on the right, what we've done is we've taken data from wetlands all the way around the world, so each dot on that plot is a wetland somewhere. And I really just want to emphasise what it shows in terms of the transition from Arctic to temperate to tropical peatlands. So the y-axis there is the rate at which carbon is accumulated in the peatlands, so the strength of what we call the carbon sink. The x-axis is related to temperature. It's not quite temperature, it's to do with growing season and light and things, but it's effectively, think of it as increasing temperature. At least that's the main relationship. As you go along that increasing temperature gradient, what you actually find is that as you move from the Arctic to the temperate area, then peatlands grow much faster in this part of the world than they do in the Arctic. As you go into the tropics, you then see a drop-off in that rate of growth. So the tropics actually accumulate, despite all this productivity, masses of biomass, they don't accumulate carbon very quickly because of the temperature has such a massive effect on the decay rates. So you can see you get this kind of gradient from Arctic to temperate to tropical, this kind of, the data is noisy, but that's essentially what it shows. And on the left, that's our reconstruction, that's our interpolation of the rate of carbon accumulation in peatlands worldwide. What we can do with that is we can run the model forward to the future and say what actually might happen in the future. So you drive a model with climate data, climate projection data, and say what happens to the wetlands in the future. Well, in the wetlands in the future, remember we're talking about the natural carbon sink, not those ones that are disturbed by human activity. In the short term, that increase in temperature results in this blue area in the north, which is the northern peatlands growing faster than they did, but in the tropics and the lower latitudes, those peatlands growing more slowly than they currently do. The balance between those at the moment suggests that by the middle of the century, we're probably going to have an increase in overall carbon accumulation in wetlands. So that's a good thing. That's taking carbon out of the atmosphere and negating some of the effects of increasing anthropogenic emissions to the atmosphere. Run it forward a couple of hundred years, 2,300 in this case, what happens is as temperatures rise further, you see greater losses in the southern, particularly in the tropics, but also in the southern part of the temperate zone, which takes out a lot of carbon. The northern peatlands still grow a bit faster, but they can't keep up. And over time, what you then see is this decline in carbon accumulation in terms of net carbon accumulation. So peatlands, wetlands act as a mitigation of climate change in the short term, but in the long term, they're going to accelerate it. So some lessons there, I think, for looking after wetlands. Talking of looking after wetlands, just come on to the extent of human impact for the future. I've already said that human impact is a major influence, particularly in the tropics and particularly in the temperate zone. This is a very recent summary of what has happened and what might happen in the near future to the overall carbon sink in wetlands. So you can see all I've done is put this axis up the side is when the situation is down here, there's a lot of carbon dioxide drawdown and there's a sink. It's a sink. When the thing's up here, it's a source of carbon dioxide. So it's just a gradient from sink to source. The units don't particularly matter, but unless anyone wants to ask afterwards. This is going through time. So in the past, gradually over the later part of the 19th century and into the 20th century, there wasn't sufficient destruction of wetlands to offset the natural accumulation in wetlands. Run it forward after about 1960 to the present day around here, you can see that overall because of that wetland destruction, wetlands are now a source of carbon dioxide. If we allow that to continue into the future, to 2100, that will only increase and get worse. So there's been a lot of discussion about how we might stop that happening. And there are already some really good green shoots, if I can use that expression, showing that actually there's quite a lot of action being taken on this and some real successes. And I've just put up the top half of the slide, if you like, is in the tropics, where you've got attempts to stop. It looks like what we've got there is a dam with holes in it. That's not quite the case. It's actually it's a fence to gradually accumulate debris, which will then slow the water down. And I'm actually standing on a proper dam. There are attempts to stop the water loss from these drain peatlands. That's in the Mega Rice project area, and also to both nurture new trees. There's a tree nursery in Indonesia, and then to plant them out to reforest some of the areas that have been damaged in the past. And the symbol in the middle is this new government body in Indonesia, which has been running now, I think, for about 5 years, and they've got a tremendously ambitious plan to restore, I think it's 2.5 million hectares of drained wetland, which is, if they do that, that would be more than anybody's restored anywhere else in the world in its entirety. On the bottom part of the slide, there's a digger there. That if you go to almost any part of the uplands where there's peat and stuff these days, you're quite likely to come across a digger. The diggers are not generally there now to dig holes, to dig ditches and drain peatlands. They're there to fill them in. And there's a huge amount of activity going on across all areas of the uplands in the UK, which results in the filling in of ditches, the blockage with dams and so on, to stop water running off these systems and to retain the carbon in the system. And that's not just in the UK, that's elsewhere. So there's lots going on which really holds out quite a lot of hope of change in the future. If we do that, this is to go back to the slide, the one on the left is just what you've seen before. If we were to employ those kinds of techniques across the areas that we know are damaged, this is what we would see in terms of happening to the carbon sink. It would return at least to neutrality, possibly to a sink. And I think that's a sign of hope for what can be done to correct this. And clearly this becomes part of the measures, the so-called nature-based climate solutions that are being employed. Afforestation is one of the most commonly known and understood ones, but wetland restoration can be an important part of that as well. So I'm just going to finish really with a couple of things as hopefully we fly along this bit of wetland in Svalbard. I come back to this other point which we haven't yet got a handle on properly, which is that we think that in the Arctic, because of that warmer, wetter environment and because of the relatively large areas of land there are available for new vegetation and wetland systems to colonise, that it's possible that these kinds of incipient wetlands will expand in the future. And we're undertaking work at the moment, this was taken this summer in Svalbard, to see whether or not these peatlands are actually spreading out, whether or not these moss patches will grow into larger areas of vegetation, and peat ultimately will sequester carbon in the future. And I think the two things to say, the really take-home messages are that wetlands undoubtedly have been already impacted by climate. They will undoubtedly be impacted by climate in the future in similar kinds of ways, and probably ways that we don't yet know about. But the biggest impacts by far are what we're having on wetlands in the past. We can use that to help mitigate some of the worst impacts of climate change. We need to do everything we can. The common phrase now, the climate emergency is upon us, and we need to do everything we can. Wetland restoration is ongoing, can be expanded, and can certainly be part of that. Thank you.
Would you have time for a couple of questions? Anybody has a question for Dan?
You might, of course, want to go and have a glass of wine and read your books, I don't know. I noticed that the Vice-Chancellor left to read her book immediately Mark had finished. I can't possibly compete with Mark, who's certainly one of the most erudite gentlemen I've ever known. So.
Okay, it's like a lecture. lecture. No one's going to...
No, it's fine.
Oh, yes.
With these new potential accumulations in the Antarctic and Arctic, could they potentially form a negative feedback and reduce carbon?
So that's what we think is happening, that they're providing that negative feedback effect. The task really is to try and quantify that. And this is a difficult area, of course, because the last message we want we don't want to send out a message which says it's fine, there's a negative feedback, don't worry about it. We think there is a negative feedback. We'd like to quantify it so we can then build it into those projections of climate change in the future. I think the point about the human disturbance is that's an area where we can accelerate that negative feedback. But yes, absolutely, we think areas like this, I mean, you can almost see it happening. That's the intriguing thing when you're there. You can see, the new growth taking place on the edges of these systems, and that's really what we've just started to collect data now to test that idea.
Thank you. Did I understand you correctly by saying when you get more wetlands, you get more carbon sinking?
Yeah.
But also there's a tension between the methane increase.
Yeah.
And how does that balance out the overall effect?
Yeah. So in terms of the balance, and that's a really important aspect to it, is the methane tends to be produced by the very wettest places and the very warmest places. So I gave a figure there for the whole of the wetland system, so that would include all the Amazon riverine systems and so on as well. They're the biggest emitters of methane. They will probably remain significant emitters of methane. We don't think that the rate of emission of methane is actually going to increase very much. In the Arctic, in the cold systems, there's the potential for greater release of methane, particularly as some of the frozen material is defrosted effectively and starts to decay. We think that's probably happening more in lake systems than it is in these wetland systems. The overall balance in terms of greenhouse warming potential, which is often the phrase that's used, probably is a contribution to warming in the short term, partly because methane doesn't last very long in the atmosphere, but over the long term, a negative effect.
Thank you.
Does volcanic activity have any impact on wetlands? Because there are areas in the northern part of the Atlantic where you would get that with debris that comes out of it.
Yes, it does have an impact on wetlands. So there's actually some studies, on what ash does to surface vegetation. I mean, the interesting thing is we know that wetlands survive through all of that and they kind of keep going, partly because you can see substantial layers of ash in many wetlands in volcanic regions. So it will disturb the system for a short while. It doesn't stop. Wetlands will just keep going as long as they're wet, as long as the plant's growing, as long as there's not too much decay, then they just keep motoring on.
Yeah, good.
Dan, if there when wetlands are being restored, is there some kind of a start-up time for them to get to kind of single functioning from a wetland?
Yeah.
I'm just wondering what the lack is potentially, what that potential impact is in reversing climate change effects. We can start with restoration.
Yeah, so you're right. It's different for every system, of course. There's no sort of single rule, and the trick is actually getting the conditions right so that things do actually get going, as opposed to they can be too wet or the nutrient conditions be too wrong and so on, too poor and so on. But actually, it's a bit like the example I showed in the Arctic, where you've kind of almost got a natural restoration experiment where the ice melts and you get a change in hydrology and then it starts to infill. It can happen very, very quickly. And actually in those Arctic systems, we have records where in the last 50 or 60 years, you've got 0.5 metre of accumulation of new material. And in fact, in many ways, at the start of the system growing or being restored, that's when the biggest drawdown of carbon dioxide is. Actually, that's when the fastest growth occurs. So it can actually have an impact very, very quickly.
Okay, so I suggest, I think, Dan, you're going to stay with us for a bit. So if you want to, I have any more questions.
I think I'm on the last train home tonight.
Oh, yes.
John's promised me a night out.
Okay, so thanks very much. You have a few questions to say, so I'm going to hand over to my colleague.
Fellow geographers, colleagues, friends, it's my privilege to be asked to propose a vote of thanks on behalf of the department and to bring to close this formal part of this wonderful celebration of 50 years of geography here at Plymouth. We've enjoyed an evening rich in memories of the development of the discipline here at Plymouth. We've looked back to the contributions of the many staff, students, collaborators who've worked so hard to build a space of teaching, innovation and research that puts student experience at its heart. We've also heard about some of the difficult, complex and pressing challenges regarding the relationships between humans and our planet that concern many of us now and are bound to preoccupy us for decades to come. A tremendous amount of work has gone into this evening, and I would like to briefly express our thanks to many of the people who've made this event a success. I'd like to start by thanking Professor Mark Blacksell for his painstaking research biography of geography at Plymouth, a fascinating and detailed account of people who've formed our collective story. A huge thank you also to our former colleague, Professor Dan Charman, now Pro-Vice-Chancellor at the University of Exeter, for your absorbing and very concerning talk about wetlands and climate change. To our Masters of Ceremony, Professors Mark Anderson, Richard Gibb, and Dr. Ruth Weaver, thank you. I would also like to make a special mention of the Royal Geographical Society, who've supported our degrees and endorsed Mark's book, in particular Dr. Catherine Souch, who was mentioned earlier, and Professor Joe Smith. A really big thank you to our wonderful student ambassadors for all the work you do representing geography at Plymouth. Special thanks particularly to Elizabeth Davenport, Amber Elliott-Jarvis, Rebecca Goff and Robbie Mill for taking part in the wonderful 50th anniversary video which is on our website and which gives the student perspective on 50 years of geography at Plymouth. Grateful thanks go to External Relations for putting together the promotional material for this event, which included a web takeover all of this week. Andy Merrington, Adam Reed and Alan Williams. Thank you also to the graphic, design and technical team who curated the exhibition in the foyer, drawn the diagrams for and typeset Mark's book and arranged its printing. Tim Absalon, Christine Cooksley, Lee Mattock and Jamie Quinn, thank you very much. I would also like to acknowledge our gratitude to the University Events team, who've organised the venue, registration and catering for the event. Shannon Healy, Samantha Davis and Alison Goodwin. We're very grateful to our sponsors for this event, Smart Applications Limited, particularly Dr. Andrew Seedhouse, who have paid for the catering and i.e. the drinks that we're just about to enjoy. A really big thank you, of course, to Professor John Shaw. From 2013 until a recent reorganisation, our head of geography, for all your hard work in organising this fantastic event. And also to Donella Bone, who's also helped with the organisation. And last but certainly not least, a heartfelt thank you to all of you for joining us in these celebrations. Past and present academic staff, research, technical, administrative staff, students and friends, we very much hope you've enjoyed your evening with us and invite you to join us for refreshments downstairs. Thank you very much.